As of yesterday, we've had our first look at some ICESat-2 data. ICESat-2 data is spatial. It has a latitude, a longitude, preferably a height. That's kind of why we're here. And what this information gives us is where these data are located. So latitude and longitude can be thought of like a horizontal location, and height is a vertical. Earth is 3D. It has a shape. What shape it is, we'll discuss a little bit as this tutorial goes on. But a lot of times we're looking at a computer screen or a paper map or someone's paper, and these are flat. And so we would like to go from our nice 3D shape with latitude, longitudes, and heights into something that we could look at on a screen, on your phone, whatever. And this is actually a kind of a complex topic, but we humans have been using maps for as long as we've gone places with ships and traveled by foot, so they've been useful for a long time. Here we're going to be using GeoPandas, which is a great set of tools for spatial data. Built upon PyProj for projections, Pandas for tables, Shapely for geometry objects. It's a really great tool set. We're going to be doing plotting in Matplotlib, and we're going to work with some raster data with Rasterio. So we'll start by making a map. This is using the built-in world coastlines that come with GeoPandas. If we inspect this GeoPandas object, we can see some sort of attributes that come with it, continents, the geometry, which is important for us. We have these things that are called multi-polygons and polygons. These are vector objects. We'll get into vector and raster and what that all means. But a vector object is basically a series of points, and whether they're connected into a polygon or not is just a level of complexity. But we can use these GeoPandas objects to create a map, which I will do again. And so what we did here is we took all those polygons that are in that GeoPandas objects of continents and all the information's in there, and we flattened it out and we put it into a projected map. We did that by projecting it. This data is into what's known as a Plat-Curie projection. It's a cylindrical projection, but with this particular projection, it's latitude as y and longitude as x. Longitude is in reference to the prime meridian, which is 102 meters east of the traditional meridian as the Earth is moved. Part of with reference and reference trends in general is they have to be continually updated as the Earth is tectonically active and things shift around. So similar to how the kilogram had to be redefined to something in first principles, the shape of the Earth has to be continually redefined as it changes. Latitude is north and south from the equator. And so this projection was cylindric. It's basically taking the round sphere of the Earth, stretching it into a cylinder and unraveling it. And so in order for it to fill the corners of that cylinder, you have to stretch out the areas as you go further and further poleward. So this map is a great map for some regions as latitudes and longitudes form straight lines, but it distorts area because you have to stretch out those areas at the poles to get it to fit that cylinder map. Other types of maps are conic projections, where you basically put a nice hat on top of the Earth or to the side of the Earth, wherever you are trying to get that cone, and then you project it that way. And then a lot of projections for polar use are planar type projections, where you project the Earth onto like a flat sheet. So every projection has positives and negatives. The Plat-Curie equirectangular is nice because latitudes and longitudes are straight lines. but it distorts area. So we can sort of look at that by plotting the normalized area as a function of space. And so just like I was trying to mention, you can have to stretch out those grid cells as you go forward. Each grid cell at the pole, especially at the pole itself, is actually area 0. And so you have to stretch it infinitely to get it to the top. And so if you're doing polar type work, this type of projection might not be the best for you. And so with that, we'll switch it over to Hannah and we'll talk about coordinate reference systems.
Hey everyone. So Tyler just touched on one component of a coordinate reference system. And this system basically tells us how we are defining our locations in space, because there are many different ways to do that. So a coordinate reference system contains a projection, which is what Tyler just talked about, going from a 3D model of the Earth to a 2D model, so we can display it on a map. It also contains a coordinate system, and that would be, for example, latitude and longitude, like the map we just produced above. We also need to have horizontal and vertical units defined. In the map above, the horizontal units would be degrees, but in other coordinate reference systems, you might have meters, and vertical units are similar in that they're often meters or feet. A coordinate reference system also contains a datum, which is a modeled version of the shape of the Earth. And this defines the origin for points or polygons or raster data that we want to display or conduct analysis on. So like Tyler noted, there are many different projections, and there's no perfect projection of the Earth. It really depends on where your study area is, and also what your goals are. You could see in the above image of projections with the conic projection that a lot of area, in many projections, area gets distorted. There are different projections that will minimize distortion in different things such as shape, area, distance, and direction. So depending on your goals, you might choose a different projection for that. And this is a comic. It's a little bit long, so I'll let you look back at it later, but it's pretty good. So I hope you do. And I'm going to post in the Slack a prompt. I want you just to think about what projections, if you're aware of using them in the past, what projections you have used and what are your favorite ones. So that's in the tutorial prompts channel of Slack. And I'll keep going, and then once we get some responses, I'll read them out loud. So using GeoPandas, we can handily see what our file has embedded in it as its coordinate reference system. So the world file that we pulled from GeoPandas looks like it's in WGS84. It's ellipsoidal, it's in latitude and longitude, and we can see the datum is WGS84. This is a lot of information to start out with, but it's super helpful. And we can see that it is an EPSG 4326. EPSG stands for European Petroleum Survey Group. And this is an organization that created codes for different coordinate reference systems to make it easier for standardization, so that if you're referring to a specific code, everyone else knows exactly what that code means. So we use them quite often. Using this geopandas.crs, it can be super helpful, but don't just blindly trust it. Sometimes data is not in the right projection or datum, and so it's important to check the metadata reports or README files that come with the data that you're using, and just to confirm that. You can also often reach out to the people who provide the data just to double check. Okay, so I have some responses on favorite projections. We've got polar stereographic, awesome, which is also EPSG 3031, I believe. UTM, also a great one. Thanks, Anthony. Lambert, Conic, conformal. These are some great examples. So thank you everyone for your responses. All right, so if we want to reproject our data to get it into maybe the same projection as other data because we want to compare them perhaps, we can do that really easily in GeoPandas as long as the reference ellipsoid or geoid stays the same, which we'll go over later. So let's use 3031, much like Jessica suggested. I think that was, oh, Anne. Thank you, Anne. So we can do that super easily by saying to CRS and providing an EPSG code, in this case 3031. And we can check that by running our the same cell as before, and we can see that it is now in the Antarctic polar stereographic projection. So it worked, yay. So now we can make another map of it and compare how these look, and you can see that they look like very different. On the left we have that cylindrical projection, and on the right we have the planar projection. And then let's zoom in on Antarctica and see how different they look. So yeah, here you can see the difference, and you can see how important it is to choose the correct projection, because the shape, the area, and if you were trying to plot direction, these are all extremely different in these two different projections, which just highlights the importance of paying attention to projections. Okay, I'll pass back over to Tyler now. Go ahead.
Yeah, so from here we've reprojected from our equirectangular into polar stereographic. This uses GeoPandas, as Hannah said, and this is a stereographic projection, which these are common in for mapping in polar regions. They've been used for a long time. A lot of legacy products for Greenland and Antarctica use polar stereographic. Some other NSIDC products use equal area, which oftentimes in these ease grids, there is a difference. Stereographic are conformal. They preserve shape, but they do not preserve area. And equal area preserve area, but they don't preserve shape. And so depending on what you're wanting to do, it may make more sense to use one or the other. So oftentimes we'll have some sort of information that we want to put on these maps. So, okay, we've reprojected something into polar stereographic, but let's add some more stuff to it. Here, what we're going to do is we're going to take the location of a research station, namely McMurdo, which is one of the main NSF stations in Antarctica, and we're going to put it on our map. We know the latitude and longitude because it's right here. So how could we not know it? It's right there. And we'll use a library called PyProj for projecting it, similar to how we did it with GeoPandas, but we're going to use just a different tool set. We're going to build coordinate reference system objects from PyProj. Here it's with this from EPSG, because we're going to be providing these EPSG codes. You can also use other ways of defining a coordinate reference system, but these EPSG codes are really easy and sort of to remember because it's just a number. You don't have to remember the exact syntax of how to build some of the other ones. So they're used pretty frequently. And then we'll build what's known as a transformer object. It's basically a black box. We have what our data is in originally, and we know what we want it to be in the end. So we have to push it through a black box to get it with all the math that it needs to go from one system to the other. And that's what this transformer is. We have our location of McMurdo in longitude and latitude, and then we'll transform it into this EPSG 3031 polar stereographic south. And so by doing that, we put it into now our units as opposed to degrees are in meters. They're in meters in reference to the South Pole. And we have our McMurdo station, which is next to the Ross Ice Shelf. Neat. So geospatial data comes in two flavors, vector and raster. Vector data is a bunch of points. These points can be connected into lines, and these lines can be connected to create polygons. Polygons can be in groups to have multi-polygons, lines can be in groups to be multi-line, and points can be in multiples, be in multi-point. You can think of ICESat-2 as a multi-point, at least in the along track data. Raster data is composed of individual grid cells. It's like imagery or digital elevation models, or our gridded ICESat-2 products, such as ATL 14 and 15, or 20 and 21, I think, whatever these sea ice ones are. And so they have different applications and uses. And so another prompt that we will put in Slack is, what are you more familiar with? Are you more familiar with using vector data, or are you more familiar with raster data? And then how do you use data? Are you more often using command line tools or Python, or do you use like a GIS software where everything is more graphical? All right. So now we're going to get into some more applications. Similar to how latitude and longitude has a reference of being the prime meridian and the equator, verticals also have a reference. These are known as datums, and they also have a unit, oftentimes meters. And here, ICESat-2 base elevations are in reference to the WGS-84 ellipsoid. And it's a particular instance of the WGS-84 ellipsoid known as this G1150. This has a particular EPSG code, which is nice to know. But another way of describing heights is in reference to the geoid. The geoid is a mathematical construct, basically thinking of similar to if sea level had no dynamics, just was at rest, there was no winds, there was no anything like that, the geoid would follow sea level. But then it would also continue it on to land. A lot of elevations are in reference to geoid, you just don't think of them. Mountains are often in heights above sea level. And this, how would you measure sea level above land when you're far away from the sea? And it's actually in reference to the geoid. ICESat-2 products produce or provide geoid heights for putting things into geoid, and the geoid instance that is used is this WGM84 2008. Different ground-based, airborne, or satellite products can use separate datums. They can be a different WGS84 ellipsoid. They could be a different ellipsoid altogether, whether it's a global base, such as WGS84, or one that's specific to a region. So there's a North American ellipsoid that's better fit the geoid regionally, but less globally. And so it's important if you're comparing heights that you are in the same datum, the same ellipsoid, or if you're in a geoid, the same geoid. We have a advanced tutorial that we put together that goes into more minute points on this, because it can be important to make sure that you're not having elevation change that's actually just due to datum shifts. And so a lot of the times when we're doing land ice height, we can just keep it in ellipsoidal, but if you're doing anything in reference to ocean or sea level, or even just terrestrial mapping, you may need to be in reference to geoid. So let's get some ICESat-2 data. We just sort of picked one at random, and we're going to download it from the National Snow and Ice Data Center. we're going to be using ATL06, which is the land ice product. It takes all those nice global photons for land ice regions, chunks them up into overlapping 40-meter segments. This should say longitude. Don't worry about that. It's amazing, like you ever print a poster and you think it's perfect, and then you put it up and then you immediately see your misspelling. That's what just happened right here. So we're going to use X-ray to open this data set. We're going to be looking at one of the particular beam groups. X-ray is nice because we can inspect things on the fly, and we can see that, look, there's variables in here. Ben went over some of them, such as the quality summary, the land ice height, the errors in land ice height, the segment ID, which is a identifier that increases from the equator, and then our correlated geolocation uncertainty. We'll take a particular time slice of it, just for making it sort of simpler to look at. And then we can put it into a geodata frame, which will look just like we did when we looked at the world coastlines. But as opposed to it being polygons and multi-polygons, we have a bunch of points. Each one of these is a latitude and a longitude and a height. These have a delta time. Delta times in ICESat-2 are GPS seconds from January 1st, 2008, and they increase monotonically from there. And luckily, we haven't had any leap seconds, so everything's fine and dandy with times. And then we can start to visualize what these look like. Here, we're going to use fancy interactive plotting with HV plot. And so we can take our ATL06 data and we can inspect it. We can hover over it. We can see what every height is. That's pretty neat. But this is still in equirectangular. This has X is longitude and Y is latitude. And so we might want to change that into something else to compare it. So we can use those same two CRS, the two coordinate reference systems that we used for the world coastlines, but we can do it with this point data. The syntax is exactly the same. It's .2CRS and then whatever the EPSG code is, or other ways of describing coordinate reference system. Head with a pandas and geopandas object allows us to inspect it. And so we make sure that our coordinates here, these points, are no longer in degrees, but they're in these big numbers that are meters. So we can scroll back real quick. Degrees, meters. Okay, they look different. And we did this so that we can compare it with a digital elevation model. Here we're going to download some data from the Copernicus DEM, which is a global DEM provided in a nice S3 bucket, pretty nice to read. And we're going to use X-ray again, and we're going to use the raster package Rio X-ray for reading this data set. X-ray again is really nice as it lets you inspect the data before you do anything with it. So we can see that this has one band, and then it has an X and a Y. Raster data is a series of pixels or grid cells. And so we can see how many grid cells are in the X, how many grid cells are in Y. And then there's bands. For visible imagery, oftentimes it's red, green, and blue. But there's also multispectral that goes into bands that we cannot see as humans. Or it could describe here, which is an elevation. So we're doing what it would be similar to false color imagery to take this DEM and plot it in colors. So this DEM is also in equirectangular. It's got longitude as X, latitude as Y. And so as we've thought about before, it's like, wait, as we go forward, that means this is going to be stretched more and more and more. So this DEM is distorted because the areas of each of these grid cells changes as we go more and more poleward. And so similar to what we were wanting to do before is we want to be able to look at it with as minimal distortion as possible. We'll project it again. This raster data already came with a coordinate reference system. It was in equirectangular 4326. And then we can take it and reproject it with X-array. What we're going to do is we're going to project it into a polar stereographic. When you reproject a raster, it's going to do some sort of interpolation. It's going to take a bunch of grid cells that are in one projection and it's going to reinterpolate it to another one. There's different levels of degrees of interpolation, and then there's different interpolation methods. Here we're going to be using a resampling method that's bilinear, and then we'll put it into this polar stereographic view. So our DEM reprojected is now all tilted. It's got it in meters, and it looks like this. And similar to with our ATL06 data, we can hover over it. We can inspect the values interactively. We can zoom to a box. Neat. And we can take our ATL06 data that we had before, reproject it, and we could plot it on top. All right, I think at this point, we're switching it back to Hannah. Is that right?
Yeah.
Yeah.
And I'll try to go slightly faster, I guess, because it's getting close. Well, yeah, we're a little bit over. So as we've mentioned, as Tyler mentioned earlier, 3D reference systems include these datums. So vertically, our heights are in reference to a datum. And there are many different datums that are in use. Two common ones are the ellipsoid and the reference geoid, which again, we briefly touched upon earlier. So the Earth is definitely not a perfect uniform sphere, but that is the simplest model of the Earth. One more level of complexity is that the Earth can be modeled as a slightly flattened ellipsoid with a polar axis that's 22 kilometers shorter than the equatorial axis, which you don't really need to know, but just know that it's slightly, it can be thought of as a flattened ellipsoid. Another level of complexity is that the Earth's shape can be described with a reference geoid. And the reference geoid is basically a surface that at every point on the Earth it has the same amount of gravity. So because the Earth isn't a perfect sphere or ellipsoid, and different places on the Earth have denser, made of denser material, the an equal gravity surface around the Earth can be approximated with the geoid, and that is approximately sea level when you ignore tides and winds and things like that. So in the figure below, you can see the difference between the ellipsoid and the EGM 2008 geoid height. And you can see that their heights vary by about negative to positive 100 meters. So that's quite a bit of difference globally between these two different vertical references. And an easier way to think about these things is that an ellipsoid can be considered a simplification of a geoid. There are a number of different ways to change your geoid. Oh, and this is a GIF of what the Earth actually looks like. So you can see that it's pretty lumpy looking and definitely not a perfect sphere or ellipsoid. It can look like a potato or a lumpy orange, I think, as someone said in the Slack, an old orange. So we're going to go quickly through this. It gets complicated quickly, and I just want to say that I think it can be really helpful to go back through this tutorial at the end or after the maybe after the tutorials today to try to review. This is all really complicated stuff, and I would not expect anyone to completely understand it after 1.5 hour tutorial. I know I'm still learning a lot about projections and datums. So don't feel like you're alone if you feel a little bit overwhelmed by all this information. So we talked about EPSG codes, and we mostly talked about 2D EPSG codes. In this line here, we have EPSG 4326 plus 3855. That's called a compound coordinate reference system. So basically you have the horizontal 4326 and then the vertical would be 3855. So it's good to be aware that some EPSG codes are only are two-dimensional. I think I want to just get past this. We should keep going. So the GDAL, okay, yeah. We'll go quickly through this as well. So here we're going to convert from geoid to ellipsoid height. We can use GDAL, which is a really useful package for geospatial data and reprojections and vertical transformations. We're going to reproject a subset of the Copernicus DEM into EPSG 7661. And this requires using what's called a vertical shift grid, which is, it's basically, I would think of it as a grid that has, similar to the image we showed earlier with the differences between the geoid and the ellipsoid with the green and blue map we showed earlier. It's similar to that, so that you would apply this shift to the geoid to get it into the ellipsoid height. There is, I think, there should be a link somewhere in this tutorial to Proj, which has a repository of these vertical shift grids. Yeah, perfect. So something to look into that we don't want to go too deeply into right now. Let's see. So yeah, Tyler, I don't know if we want to, how far deep you want to go into this.
So basically what Hannah was showing is that we can take multiple EPSG codes, add them together, and then the software will take those and build either a coordinate reference system that we want to go to or from. Here we're going from a compound projection into this 7661, and then using GDAL to do those coordinate shifts. We didn't have locally this vertical shift grid, but it knows that where they are on this proj.org, and it downloaded them for us in the background and then applied it. In the end, we have this new DEM in the new projection, and that takes us to the end. So we've gone through a lot, going from why would we project data in the first place to touching on vertical datums and the different types that you might see. We've shown a few different ways of reprojecting data, whether it's a raster with rasterio and a rasterio X-ray, GeoPandas and PyProj, and we've shown how to construct some compound pipelines for projecting from specific data sets. I know it's a lot to go through, and we have a bunch of material that can hopefully help you on your way. But the main thing to get away is if you're comparing heights with anything else, make sure they're in the same datum and same projection, or else you might run into some shifts that are actually just due to different projections and datums. So thanks.